In class exercise 4, chapter 4. Replace the loading on the frame by a single resultant force. Specify where its line of action intersects with a vertical line along member AB measured from A. So we need to calculate here, we need to replace this multiple forces by a single resultant force. So our final answer is something like this. So we are looking for single resultant force. Fr is for resultant, x is the x component, and Fry is the y component. So we would like to replace all these four forces by one resultant force with its horizontal and vertical components, and the location of this force, that is this point from A. This is what we need to determine in this problem. How far this force is acting on this beam. And this is called equivalent force system. So we can reduce multiple forces to a single force. Now, first step is we need to make sure that we resolve all the forces into horizontal and vertical components to simplify our calculation. So this 900 can be reduced to 3 by 5th of 900, which is 540 newtons horizontal component, and vertical component will be 4 by 5th of 900, so that is 720 newtons. This 400 can be reduced to 4 by 5th of 400, which is 320 newtons, and vertical component is 3 by 5th of 400, which is 240 newtons. So now we don't consider like this and this component like forces, but we will instead consider the horizontal and vertical components. So we define our coordinate system: x going right and y going up are positive, and moment counterclockwise is positive. So this is our new coordinate system assumption, where we have defined the linear axis as well as rotational positive directions. So we first thing is we would like to find the equivalent resultant horizontal and vertical force. So we apply this equation: sum of forces in x direction is equal to resultant forces x component. So we consider only x forces here. So x forces are only two, 540 and 320. 540 is positive, 320 is negative as per our direction assumption. So this is 220 newtons. Then sum of forces along y-axis gives us resultant component's vertical force, and there are only two forces here, and those are sorry, there are four forces here: 400, 600, 250, and 720. So if if force is acting up, then it's positive. So it's minus 400 plus 600 minus 720 plus 240. So as a result, we get minus 280 newtons. Means our resultant force will act in the y direction. The y component of the resultant force will act in the negative y direction. And this is Frx. Okay. But now the question is, where are these forces located along this line AB? So for that, we will apply so these are the equations that we are applying. Sum of forces gives us the resultant force. That's equation number 1. And the second one is sum of moments about point A should be same as sum of all the couple moments about point A plus sum of the resultant forces moment or resultant moment about point A. This should be MR. MR. Okay. So let's redraw this diagram now. So we have this L-shaped structure where point B is here, point A is here, which is like close to ground, and then we have Frx, which is 220 newtons, and we have Fry, which is minus. Sorry, now because we are indicating the force in the negative direction, we can write the positive number 280 newtons. No, don't put the negative sign here because graphically we have indicated that it's acting down, Fr. Okay. But we don't know its location, so we assume that this is located at A, distance from point A. So what should happen now is if this new system and this previous system are equivalent, then the net moment at point A should be same. So net moment calculated because of all the forces here about A should be same as net moment because of this forces about A. Now the moment includes both force and distance, so that's where A will be multiplied in the equation of moment with the force, and we will be able to solve for A. So now the net moment at A in both the systems should be the same. Now when I say both the system means multi-force system and resultant force system. Okay, so sigma, now for that matter, multiple force system is sigma sum of moments about A is equal to sum of resultant moment about A, like force because of this second system about A. So this is one, this is two. So multiple forces here, their moments about A means we need to find out, we just need to calculate the moment of each and every force about point A. There is no moment of 720 about A because it passes through A. 540 has moment which is 540 multiplied by 1.5 plus 1 which is 2.5 and clockwise. So that's negative. 320 multiplied by 1 counterclockwise, so it's positive. 600 multiplied by distance from A, which is zero point 0.5 clockwise, so it's negative. And 400 multiplied by this distance, which is 1.5, and that's counterclockwise, so it's positive. So let's substitute everything for 1 is coming from the multiple system. So this is now 400 multiplied by 1.5 minus 600 multiplied by zero point 0.5 minus 540 multiplied by 2.5 plus 320 multiplied by 1. Okay, so these are different couple moments. And the moment because of the resultant force components at A is this force moment about A, which is 0 because it's passing through A. It's only Frx multiplied by A, and that's clockwise, so it's negative. So this is minus Frx multiplied by A. So everything here we know except A. So Frx is 220 multiplied by A. Now this negative sign is because this results in clockwise moment about A. So it results in clockwise moment, and that's why it's negative. So the whole left side equation is minus 730. So A we get is 3.31 meters. And that's what we are looking for, 3.31 meters. What this means that we have reduced this multiple forces to only one horizontal and vertical force that are the components of the resultant force acting at 3.31 meters from A, such that the net effect, external effect at A is same in both the cases. Okay, and that's why it's called, this system is called equivalent force system.